We are living in an era of big data, a time in which computational power and engineering tools allow AI machines to learn on their own. However, when it comes to data sharing agreements, are all data available to all applicants? The answer is no. Data sharing relates to corporate security and confidentiality concerns. What's more, data sharing often conflicts with data privacy issues. AI applications must comply with privacy protection laws such as the General Data Protection Regulation (GDPR). Traditional machine learning requires training data to be aggregated into a single machine or in a data center. The reality is, data often exists in isolated silos. With privacy concerns, data cannot be easily shared across multiple parties. This centralized training approach is at odds with privacy preservation. Federated AI, a decentralized machine learning approach, enables users to collaboratively learn a model while keeping sensitive data and private data. In this video, we explain three main types of federated AI: horizontal federated learning, vertical federated learning, and federated transfer learning. As an example, a financial company wants to improve its credit estimation model by studying client consumption behaviors. However, such private data are stored in each client's local account and cannot be shared to a financial company under GDPR. By leveraging horizontal federated learning, clients first download the currently initialized model parameters from the server. Then, each client computes and updates by using the local private training data. After training, clients upload the new gradients to the server. The server then aggregates all client updates into a new and improved model. The entire process iterates until convergence. Gradient values can leak private information when the data structure is publicly known. To address this issue, we can secure the gradient through techniques such as homomorphic encryption, so that the server does not learn any information about the gradient it receives, while still able to perform model aggregation. Horizontal federated learning is suitable when two parties share large overlapping features, but with mostly different sample IDs. What if the two parties have a lot of overlapping user IDs, but their features are different? Suppose a bank and an e-commerce company are doing business in the same city. Their customers are mostly local residents. Since they are different business, the overlap of features is limited, but customer bases are similar. In this scenario, vertical federated learning can help them collaborate. It consists of two major steps. Step 1. Encrypted sample alignment. Vertical federated learning uses encryption-based user sample alignment techniques to identify common uses shared by both parties without exposing their own identifications, constructed by uniting the features of these common uses. Step 2. Encrypted model training. To ensure data confidentiality during training, a trusted third party, the collaborator C, is established for encrypted model training. It can be further divided into 4 steps. Firstly, C distributes the public key to the two data owners, A and B, for them to encrypt the data that need to be exchanged during training. Secondly, A and B exchange the intermediate results to calculate the gradients. Thirdly, A and B calculate the loss and send back the results to C. C calculates and describes the combined gradient. Lastly, the combined gradient is sent back to A and B, which respectively update the local mode parameters. What if we cannot find a trusted third party? Can we remove the collaborator C? The answer is yes. By carefully designing a secure data exchange protocol, we can establish vertical federated learning with just 2 parties. What if there are not enough matched sample IDs and features regarding the 2 collaborating parties? Suppose there are 2 parties, one is a bank doing business in China, and the other is an e-commerce company doing business in the US. There are few overlaps in both users and features. In such cases, we introduce federated transfer learning to allow the party with more well-labeled data to help the other party perform prediction tasks. The basic idea is that a party B can use the overlapping sample C to predict the missing features in B's data that do not belong to party A. Once B has established a model, B sends the model to A in a secure way so that A can leverage it to predict the labels for other samples in A's dataset. In the other way around, A performs a similar procedure to help B. With these 3 techniques, federated learning can cover the entire feature and sample space. This allows us to build a federated learning ecosystem that ushers in a new generation of AI technologies that can engender trust with users through privacy by design.